Our planet, Earth, has a story to tell. It's a story written over billions of years. This story is about change, especially climate change. The Earth's climate has never stayed the same. It has swung between periods of warmth and intense cold, shaping the world we know. Paleoclimates are the climates of Earth's past. They are clues left behind by a changing planet. These clues help us understand how and why the climate changed throughout history. Just like detectives, scientists piece together these clues. Imagine a world covered in vast ice sheets. This was Earth during periods called ice ages. These icy periods have come and gone, leaving their mark on the land. By studying paleoclimates, we gain valuable knowledge about these dramatic events. The story of Earth's climate is more than just ancient history. It holds lessons for us today. By looking at past climate patterns, we can better understand the changes happening now. This knowledge helps us predict and prepare for the future of our planet. The past holds the key to understanding the present and the future, especially when it comes to climate. By investigating past climates, we unlock secrets about Earth's climate system. This knowledge is crucial as we face the challenges of modern climate change. Think of it like a puzzle. Each piece of information about past climates helps us assemble a clearer picture of Earth's climate system. The more pieces we find, the better we understand how different factors interact. Imagine knowing when the next big heat wave will hit, or how much sea levels might rise. Studying paleoclimates provides valuable data that informs these predictions. This information helps us make informed decisions about our future. Understanding the past is not just an academic exercise. It's about protecting our planet for generations to come. By learning from ancient climate patterns, we can better mitigate the risks and adapt to the challenges of a changing world. Imagine a detective arriving at a crime scene. They look for clues, pieces of evidence left behind. Climate scientists do something similar. They act as detectives of the past, piecing together clues about ancient climates. But instead of fingerprints and footprints, they look for clues in nature's archives. These archives are hidden in unexpected places. They are found in the icy grip of glaciers, the silent growth rings of trees, and the layers of sediment at the bottom of lakes and oceans. Each archive holds a record of past climates waiting to be deciphered. One of the most valuable archives is found in ice cores. These long cylinders of ice are drilled from glaciers and ice sheets. They contain tiny bubbles of ancient air trapped within the ice. By analyzing these bubbles, scientists can measure the composition of the atmosphere from thousands of years ago. Another clue lies in the rings of trees. As trees grow, they form annual rings that reflect the climate conditions of each year. Wider rings indicate favorable growing seasons, while narrower rings suggest harsher conditions. These rings provide a year-by-year record of climate variations. Imagine a time capsule buried deep within a glacier, preserving a snapshot of the past. That's what ice cores are, frozen time capsules that hold a wealth of information about past climates. These cores are formed by the gradual accumulation and compression of snow over thousands of years. As snow falls, it traps air bubbles and particles from the atmosphere. Over time, the weight of the accumulating snow compresses the lower layers, turning them into ice. The trapped air bubbles become preserved, offering a glimpse into the atmospheric composition of the past. Scientists extract these ice cores by drilling deep into glaciers and ice sheets. The deeper they drill, the further back in time they can go. Some ice cores extend back hundreds of thousands of years, providing an invaluable record of Earth's climate history. By analyzing the chemical composition of the ice and the trapped air bubbles, scientists can determine past temperatures, greenhouse gas concentrations, and even volcanic eruptions. Ice cores have revolutionized our understanding of past climate variations. Section 3. Tree Rings, Nature's History Books. Trees are silent witnesses to the passage of time, recording their growth in annual rings that tell a story of changing climates. These rings, visible in a cross-section of a tree trunk, hold clues to past rainfall, temperature, and even forest fires. Each year, a tree adds a new layer of wood beneath its bark. This layer, called a growth ring, reflects the growing conditions of that year. In years with ample rainfall and favorable temperatures, the ring is wider. In drier or colder years, the ring is narrower. By carefully measuring the width and other characteristics of tree rings, scientists can reconstruct past climate patterns. This method, called dendrochronology, allows them to create timelines of climate variability spanning hundreds or even thousands of years. Tree ring data is particularly valuable for understanding regional climate variations. It can also help scientists study the impact of past climate change on forests and ecosystems. Section 4. Secrets in Stone and Water. The Earth's surface is constantly changing, with rocks eroding, sediments accumulating, and water bodies leaving their mark. These processes create a rich tapestry of geological and hydrological records that hold secrets about past climates. Sedimentary rocks, formed from the accumulation of particles over time, often contain fossils and chemical signatures that reflect the environmental conditions in which they formed. For example, the presence of certain marine fossils can indicate past ocean temperatures and salinity. Lake and ocean sediments also preserve evidence of past climates. As organic matter and minerals settle to the bottom of these water bodies, they form layers that trap pollen, isotopes, and other indicators of past climate conditions. By analyzing these geological and hydrological records, scientists can piece together a detailed picture of past climate changes over millions of years. They can track the advance and retreat of glaciers, the rise and fall of sea levels, and the evolution of Earth's climate system. Section 1. Frozen Giants, A History of Ice Ages. Imagine Earth transformed into a giant snowball. Our planet has experienced extreme cold several times. These periods, known as ice ages, last millions of years and reshape Earth's geography. Scientists study these ice ages to understand climate dynamics and future changes. Earth's deep freeze, the Huronian glaciation. Over 2 billion years ago, Earth experienced the Huronian glaciation. This severe ice age lasted 300 million years. Ice sheets stretched from the poles to the equator. The rise of oxygen in the atmosphere is a leading theory. This event paved the way for new life forms. Section 3. Snowball Earth, the Cryogenian Period. Imagine a time when Earth resembled a giant snowball, its oceans frozen over and its continents buried beneath thick ice sheets. This is not a scene from a science fiction movie, but a glimpse into the Cryogenian Period, one of the most extreme ice ages in Earth's history. Occurring between 720 and 635 million years ago, the Cryogenian Period witnessed the most severe glaciations ever known. During this time, ice sheets extended all the way to the equator, earning this period the nickname Snowball Earth. The exact causes of this extreme glaciation are still debated, but likely involved a combination of factors. One theory suggests that a decrease in volcanic activity led to a reduction in greenhouse gases in the atmosphere, causing global temperatures to plummet. Another theory points to the breakup of the supercontinent Rodinia, which may have altered ocean currents and disrupted heat distribution around the planet. The Snowball Earth events had a profound impact on life. While some organisms managed to survive in isolated pockets of warmth such as hydrothermal vents, many others perished. However, this period also saw the rise of multicellular life, suggesting that these extreme conditions may have played a role in driving evolutionary innovation. Section 3. Snowball Earth, the Cryogenian Period. Imagine a time when Earth resembled a giant snowball, its oceans frozen over and its continents buried beneath thick ice sheets. This is not a scene from a science fiction movie, but a glimpse into the Cryogenian Period, one of the most extreme ice ages in Earth's history. Occurring between 720 and 635 million years ago, The Cryogenian period witnessed the most severe glaciations ever known. During this time, ice sheets extended all the way to the equator, earning this period the nickname Snowball Earth. The exact causes of this extreme glaciation are still debated, but likely involved a combination of factors. One theory suggests that a decrease in volcanic activity led to a reduction in greenhouse gases in the atmosphere, causing global temperatures to plummet. Another theory points to the breakup of the supercontinent Rodinia, which may have altered ocean currents and disrupted heat distribution around the planet. The Snowball Earth events had a profound impact on life. While some organisms managed to survive in isolated pockets of warmth such as hydrothermal vents, many others perished. However, this period also saw the rise of multicellular life, suggesting that these extreme conditions may have played a role in driving evolutionary innovation. Section 4. From Ice to Green, the Paleozoic Icehouse. Following the extreme glaciations of the Cryogenian period, Earth entered a period of relative warmth and stability. However, the planet's icy grip was far from over. During the Paleozoic era, spanning from 541 to 252 million years ago, Earth experienced another significant ice age, though not as severe as the Cryogenian. This period, often referred to as the Paleozoic Icehouse, was characterized by fluctuating but generally cooler global temperatures compared to the preceding period. Ice sheets expanded and contracted, influencing sea levels and shaping the evolution of life on Earth. Several factors contributed to this cooler climate. One significant factor was the position of the continents. During the Paleozoic, the supercontinent Gondwana drifted over the South Pole, leading to the formation of large ice sheets. Additionally, changes in atmospheric composition, particularly fluctuations in carbon dioxide levels, played a role in regulating global temperatures. The Paleozoic Icehouse witnessed the diversification of life in the oceans and the colonization of land by plants and animals. The fluctuating climate, with periods of glaciation followed by warmer interglacial periods, likely influenced the evolution of new species and the distribution of ecosystems. Section 5. The Quaternary Ice Age, a world of ice and change. We now arrive at the most recent ice age in Earth's history, the Quaternary Ice Age. Beginning around 2.6 million years ago and continuing to this day, this period has witnessed dramatic swings between glacial and interglacial periods, shaping the world we know today. During the Quaternary Ice Age, vast ice sheets, sometimes miles thick, advanced and retreated across North America, Europe, and Asia. These glacial cycles had a profound impact on Earth's surface, carving out valleys, creating lakes, and transporting massive amounts of sediment. The Quaternary Ice Age also witnessed the evolution of our own species, Homo sapiens. Our ancestors were forced to adapt to changing environments, developing tools, clothing, and social structures to survive the harsh conditions. The challenges and opportunities presented by these climate fluctuations likely played a role in shaping human evolution. While we are currently in a warmer interglacial period, the Quaternary Ice Age is not over. Understanding the causes and consequences of these past glacial cycles is crucial for predicting future climate change and its potential impacts on our planet and our species. Section 1. The Climate Puzzle. Unraveling the Causes of Ice Ages. Imagine a giant puzzle, its pieces scattered across time. Each piece represents a factor in Earth's climate system. Scientists work tirelessly to assemble this puzzle. Understanding these causes is crucial. Ice ages are triggered by a combination of factors. They disrupt the delicate balance of Earth's climate. Key players include Earth's orbital variations and plate tectonics. Milankovitch cycles influence solar radiation. Plate tectonics alter ocean currents and trigger volcanic eruptions. Earth's orbital dance. Imagine Earth engaged in a slow, graceful dance around the Sun, its movements influenced by the gravitational pull of other celestial bodies. This cosmic choreography, known as Milankovitch cycles, shapes Earth's long-term climate patterns. Named after Serbian geophysicist Milutin Milankovic, these cycles describe three main variations in Earth's orbit and rotation. Section 3. Plate tectonics, reshaping the planet, reshaping the climate. Section 4. Greenhouse gases, the thermostat of our planet. Section 5. Feedback loops, amplifying the cooling effect. Section 1. Sculpting the land, the physical impacts of ice ages. Imagine a giant sculptor, its icy fingers carving and shaping the Earth's surface over millennia. These periods of intense cold leave a profound and lasting impact on the planet's physical features. Section 2. Oceans in retreat. Sea level changes and coastal transformations. Imagine coastlines redrawn, vast areas of land submerged or exposed as the oceans rise and fall. During ice ages, massive amounts of water are locked up in ice sheets on land, causing a significant drop in sea level. Section 3. A chilled biosphere. Life's adaptations to glacial conditions. Imagine a world where temperatures plummet, ice sheets advance, and landscapes transform. The chilling grip of these glacial periods forces organisms to adapt, migrate, or face extinction. Section 4. The rise of new species. Evolution in the face of ice. Imagine isolated pockets of life, separated by advancing ice sheets, evolving along different paths. While these periods present significant challenges, they also act as engines of evolution, driving the emergence of new species. Section 5. From glaciers to deserts, shaping Earth's landscapes. Imagine a world in constant flux, its landscapes transformed by the ebb and flow of ice. These periods of intense cold not only sculpt mountains and carve valleys, but also leave a lasting impact on the distribution of deserts and the formation of lakes. Section 1. Echoes of the past, parallels between then and now. As we delve into Earth's ancient past, exploring the icy realms of past ice ages, we uncover more than just geological and biological history. We find echoes of the past, whispers of change that resonate with the climate challenges we face today. Section 2. The unnatural acceleration, human influence on climate. While Earth's climate has always been in flux, the rate of change we observe today is unprecedented in human history. This acceleration is not the result of natural cycles, but rather the consequence of human activities, particularly the burning of fossil fuels. Section 3. Lessons from the ice informing our climate future. The icy archives of Earth's past, preserved in glaciers, ice sheets, and sediment layers, hold invaluable lessons for navigating our climate future. By studying past climate changes, their causes, and their impacts, we gain insights into the potential consequences of our actions and the choices we can make to mitigate future risks. Section 4. The urgency of now acting on the knowledge of millennia. The Earth's climate history, etched in stone, ice, and the very rings of ancient trees, speaks to us with a profound urgency. It tells a story of change, adaptation, and the interconnectedness of Earth's systems. Section 1. A Journey Through Time, a Vision for the Future. Our exploration of paleoclimates has taken us on an incredible journey through time. We've delved into Earth's ancient past, witnessing the ebb and flow of ice ages, the dramatic transformations of landscapes, and the remarkable resilience of life in the face of environmental change. This journey, however, is not just about looking back, it's about looking forward, using the knowledge gained from millennia to shape a more sustainable future. Imagine a world where ancient ice cores become crystal balls, their layers of frozen history providing insights into future climate scenarios. By deciphering the secrets held within these icy archives, we gain a deeper understanding of the complex interplay of forces that drive Earth's climate system. This knowledge empowers us to make more informed decisions, to develop strategies for mitigating the risks of climate change and adapting to its unavoidable impacts. It allows us to anticipate challenges, to prepare for sea level rise, to develop drought-resistant crops, and to build more resilient communities. The study of paleoclimates is not just an academic pursuit. It's a vital tool for safeguarding our planet's future. It provides us with a roadmap, guiding us towards a world where we live in harmony with nature, where we respect the delicate balance of Earth's systems, and where we leave a legacy of sustainability for generations to come. Section 1. A Journey Through Time, a Vision for the Future. Our exploration of paleoclimates has taken us on an incredible journey through time. We've delved into Earth's ancient past, witnessing the ebb and flow of ice ages, the dramatic transformations of landscapes, and the remarkable resilience of life in the face of environmental change. This journey, however, is not just about looking back, it's about looking forward, using the knowledge gained from millennia to shape a more sustainable future. Section 2. The Past, as Prologue, Predicting and Preparing for Change. William Shakespeare famously wrote, "What's past is prologue." This rings true for understanding our planet's climate. Past ice ages and sea level changes remind us that change is constant. Studying these events helps us predict and prepare for future changes. We can develop better climate models and strategies. The past serves as a prologue to the future. We are active participants in shaping our planet's destiny. Section 3. Our Legacy, Our Responsibility, Stewards of a Changing Planet. As we conclude our journey, we are left with a profound sense of responsibility. The planet we inherit is dynamic, shaped by natural forces and human actions. Our choices now will determine Earth's climate future and our legacy. The knowledge we've gained shapes the future. It empowers us to make informed decisions. This responsibility extends beyond reducing our carbon footprint. It requires a fundamental shift in our relationship with nature. It calls for a commitment to sustainable practices and innovation. The Earth's climate has changed dramatically throughout its history. We have the tools to ensure a future where humanity thrives in balance with nature. Let our journey inspire us to become the caretakers our planet needs.